Hello. Okay, so this video is intended to give you a sense for what you're going to do in the lab on Tuesday. This equipment that's under the camera right now, this is the timer you're going to use. These things are called Photogates right here. And I want to describe how all of this works. So the timer can work in a lot of different ways. Let me move the Photogates to the side for a second. The timer, there's an on switch for the timer over here. Lights come on when the timer's on. There are many different settings. I want to show you first what you can do with the timer by itself. You can use it as a stopwatch. We're not going to use it this way, but you can. If you go to the stopwatch mode and just press A, and again to stop, you can run it as a stopwatch. Reset the time, start, stop. Press it again to keep going and stop, stuff like that. So you can use this as a stopwatch. There's a couple other modes that we won't use. The one we are going to use is interval. This here is called a Photogate. You can see there's a green light on there. That means that the Photogate's on and has not been triggered. There's a telephone cord that goes from the Photogate to the timer box. And this Photogate here is plugged into the A port. So that's my A Photogate. I have another Photogate here. It's also on, you can see the green light. It has a white cord, and it's plugged into the B port of the Photogate. So, of the timer, excuse me. So two Photogates plugged into different ports of the timer box. And if I turn on the light for A, there's a number there. I'm going to reset it. The way that the Photogate works is, if you look closely at it here, you can see there's a tiny little slit there. And on the other side, there's another tiny little slit there. Inside of the plastic casing of the Photogate, there's a little infrared laser that points right out of that slit. And there's a little infrared receiver on this side that receives the laser. So what the Photogate does is it checks to see if the laser is broken or unbroken. If the receiver is receiving a signal, it knows that. If it's not receiving a signal, it knows that. And so this is how the Photogate times things. So when I have the A light on, if I break the laser's path, the timer starts. If I remove my hand so that the laser is again unbroken, it stops timing. So again, to show you, start timing, stop timing, start timing, stop timing. And what this time measures, which I'll call the A time, what the A time measures is how long the laser has been broken for in the A Photogate. So start timing, stop timing. And you can see it just overwrites. So it starts back from 0 every time I do this. So you don't necessarily have to reset every time, but it can be convenient. So the A time, when the A light is lit up, measures how long the laser is broken for in the A gate. I can also look at the B time too. So I've got my B timer. So now I'm looking at things having to do with the Photogate that's plugged into the B port of the timer. And the B time is the same as the A time for the B Photogate. So if I break the plane of the laser for the B Photogate, it starts timing and stops timing. You can see here also, if you look at the light up here in the corner, when I break the laser's plane, that light turns red. And when I unbreak it, it turns green. That's a visual way to get a sense for when the timer is active and not. Okay, so the B time is how long the B gate's laser is broken for. Also, so A and B time are equivalent, just with different Photogates. Let me reset everything. There's another option here too, which is the A-B time. If I have both A and B selected, I measure something different. So here's my A gate. If I break the plane of the A gate, it starts. If I remove my hand, it keeps going. So let me try that again. I think I screwed it up. Let me try it again. So I put my hand in, remove my hand, it keeps timing, which is different than before. This time will not stop until I break the plane of the B laser. So when I do that, I put my hand in here, the time stops. So this is measuring how long it takes between when the A gates laser is broken to when the B gates laser is broken. Let me show you that again. So another example, if I break the A gates laser, timing starts. If I break the B gates laser, timing stops. We'll call this the AB time. It's kind of hard to understand why that would be useful in this abstract sense. But when I show you the setup, which I will do in just a sec, you'll see how we're going to use that. So let me move over to the setup so you can see what it looks like and you can see the use of these Photogates in context. All right, so here's the setup that you're going to be working with. There's an incline track. I've got the timer box here, and I've got the two Photogates hooked up to the timer box. So I've got the A gate at the higher side of the ramp, and I've got the B gate here at the lower side of the ramp. So you can see how the Photogates might be useful for timing here. So when I'm timing, what I've got is this car also. There's a little flag on top of the car, and the reason for the flag is to trigger the Photogates. So if I just do kind of a demo of what's going to happen, the car is going to roll down the incline, and you'll be timing it with the Photogates as it goes. The flag triggers the Photogate while the car passes under the Photogate. So this way the car can move unobstructed, it never hits the Photogate, but the Photogate still sees the car. And it's just this flag that triggers the Photogate. So the A time is the time it takes for that flag to pass through the laser. The car keeps going, and then same thing with the B gauge. So the flag passes through the laser while the car goes underneath the photogauge. So the B time is how long it takes the flag to pass through the laser of the B photogate. Also, the AB time, which starts when the laser is triggered for A and stops when the laser is triggered for B, is how long it takes for the front of the flag, which first triggers the photogauge, to get from here to there, if that makes sense. So A time is how long it takes the flag to pass through this laser. The B time is how long it takes the flag to pass through this laser. And the AB time is how long it takes the flag to go from here to there. Okay, so let me do a run. We'll take some data and then talk about how we can manipulate it. So what it'll look like is you'll have the car up here at the top. You'll be taking several trials for each setup. So I would encourage you to start the car from the same place every time. Doesn't have to be right where the photogate is, doesn't matter. The way I'm doing it is I'm putting the end of the car right at the end of the track, so I feel like I can always reproduce that. And then I'll just let it go. Okay, that worked. I'll record the times. So the A time I got was 0.0729 seconds. The B time I got was 0.0462 seconds. And the AB time I got was 0.5440 seconds. I'm going to write those down and then we're going to work with them a little bit. Okay, so I've written down some of the data I got. So I got the A time, 0.0729 seconds, the B time, 0.0462 seconds, TAB, 0.5440 seconds. I also recorded the length of the flag, so the little paper flag on top of the car. I recorded the width of that. I also recorded how far it was between the A and the B photogates. I'll call that the AB displacement here. One of the things we can do with this data is use it to calculate velocities. We're only ever calculating average velocities, but that'll help us get a sense for how fast the car is moving at different points on the track. So the A time corresponds to how long it took for the flag to pass through the A gate. That's true. It's also true, same thing for the B gate, except for replacing A gate with B gate. So let me copy that. I'll paste it here and do it this way. So that's true. Same thing, except with the B gate for the B time. So if we wanted to figure out a velocity, an average velocity of the car, excuse me, when passing through the A gate or the B gate, we're looking for the displacement over the time as the car passed through the A gate or the B gate. So if I wanted to do that, let me call that VA. So VA equals the average velocity through the A gate. And if you think about it, you might realize that the displacement for the car through the A gate is just the width of the flag, because the time corresponded to how long the flag was in the A gate, and how far the flag moved while the A time was recording was exactly the width of the flag, because the time started when the front of the flag first hit the laser, and it stopped when the back of the flag left the laser. So the front of the flag traveled exactly one flag width in that amount of time. So this is equal to 6.8 centimeters, the width of the flag, over how long it took to cover that displacement, which is the A time, 0.0729 seconds. You calculate that out and you get something around 93 centimeters per second. Cool. If I want to do the B velocity, which is what I'll use to denote the average velocity through the B gate, it's the same argument. So it's the width of the glider flag over the B time, 0.0462 seconds. That's equal to 147-ish centimeters per second. As a brief sanity check, if we compare these two values, we see that the B velocity is greater than the A velocity, which makes sense because the B gate is further down the incline than the A gate. So if we're measuring velocity and we expect that the car will speed up as it goes down the ramp, then we'd expect the velocity it has near the A gate to be slower than the velocity it has near the B gate. So that checks out, that makes sense. There's one other velocity I can calculate, which is the VAB. This is the symbol I'll use to denote the average velocity from A to B. So that is, what's the total average velocity for the whole trip from A to B? So in that case, we're taking the whole displacement from the A gate to the B gate as our displacement, and the glider covered, or the car covered that displacement in the AB time. So it took the AB time to go the full displacement from A to B. So that is 65 centimeters is the displacement from A to B, and the time that corresponds with that is the AB time. If you calculate that, you get something near 119 centimeters per second. And as another sanity check, we've got three velocities, and we can think about the relationship between them. I argued that it makes sense that VB is higher than VA. VAB looks to be right around the middle between VA and VB. Not exactly, but right around the middle. So does that make sense? Well, kind of, because we're looking for the average velocity from A to B. VA represents something like the initial velocity for that trip. So this is the velocity it had right around the time it was at the A Photogate. This VB represents sort of the final velocity for the trip. That is the velocity when the car was passing through the B Photogate. This represents an average velocity for the entire trip. So it better be in between the initial velocity and the final velocity if the velocity is changing. So as a sanity check, that kind of makes sense. We're getting something that looks like we might expect. And these values, VA, VB, and VAB, we're going to use them to make sense of the way that the velocity of the car changes over time as it goes down the track. And this is the kind of analysis we'll start to do. So I hope that was helpful. And if you have any questions about the setup, I'm happy to answer them now through email or when we get into class on Tuesday. Okay, I will see you soon. Bye.